You want to model a watershed. Before a single equation runs, you have to answer a harder question. What are the pieces and how are they connected? Turning terrain, soils, land cover, and weather into a computational structure is where most modeling projects stall, not in the physics. So instead of talking about it, let's build one. For real, on screen, the upper San Pedro basin in Arizona from its gauge number alone. This is the basin's real terrain from its model files. A watershed model can't solve this as one lump. It has to be divided until conditions inside each piece are roughly uniform. Watch the hierarchy form. First, 12 subbasins, the routing skeleton. Then, inside them, the hydrologic response units. Every unique combination of land use, soil type, and slope class gets its own unit. 11,000 of them here. The HRU is the computational atom. The water balance is solved there and nowhere finer. Getting there means delineation, and delineation is the fragile step. From the elevation grid, you derive a flow direction for every cell, accumulate it into streams, and cut the landscape into catchments. Watch it happen on the real terrain. The main stem finds the valley first, then the tributaries fill in. Real terrain fights back. Pits and flats where water has nowhere to go, and flat ground where a 1-meter error changes which way the water leaves. This is the step that produces the error messages and the forum threads. There are two ways through it. You can derive everything from the terrain itself, which works anywhere but inherits every artifact in the elevation data. Or you can use a surveyed hydrography, a national dataset where the streams, catchments, and water bodies have already been mapped and quality controlled, and make the terrain agree with it. We use the second and fall back to the first only when it fails. Now watch the national data land on the basin, layer by layer. The channel network comes from NHD plus high resolution, surveyed, not guessed. The soils drape on from gSSURGO, the 2023 National Survey. 91 soil types in this basin alone. Land cover comes from NLCD, and the climate arrives as a grid. 80 PRISM cells, each carrying 25 years of daily precipitation and temperature, with solar, humidity, and wind from the National Solar Radiation Database. Every model is built from these same sources, which is what makes one basin comparable to another. The pipeline runs in order. Clip every national layer to the watershed. Build the stream topology and the catchment shapes. Delineate and form HRUs from the land use, soil, and slope overlay. Assign weather stations to each subbasin. Write the SWAT plus project files. Then, and this matters, run a 1-year verification simulation to prove the model actually executes. Attach the observed stream flow record from the USGS gauge, and stamp the whole thing with a provenance file recording every dataset version that went into it. And what do you provide? One identifier, a USGS gauge number, or a 12-digit watershed code. Around 25,000 gauges across the continental United States are available. Everything else, resolutions, thresholds, weather period, has a default that works and only becomes a choice if you want it to be. And here is what came out from one gauge number: 11,284 hydrologic response units, 350 channels, 12 subbasins, 80 climate cells, a complete, runnable SWAT plus model, and the build was measured at 23 minutes. Across our published catalog, the same pipeline spans 473 HRUs to 236,000 without rewriting anything. And the time? A small watershed builds in about 8 minutes. A mid-sized basin, 23. The Peace River Basin in Florida, 94,000 HRUs, 8,000 channels, 347 lakes and reservoirs, assembles unattended in 1 to 2 hours. The comparison that matters isn't against a faster computer. It is against the weeks of manual GIS work this replaces. A watershed model is not the end of the work. It is the beginning of it. The point of automating the assembly is that the interesting questions, the calibration, the scenarios, the contaminants, start on day 1 instead of month 3.